Hi and welcome to the video lecture series on thin film flow modeling and simulations in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Alkes and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the second part of the second video lecture on the introduction and underlying theory. And here we'll learn what the thin film approximation is and how to apply scaling and dimensional analysis to achieve it. Let us start with a thin film approximation. Now there are many thin film flow problems out there, and here are a few examples. So you will find very thin film lubricating the tooth between gear teeth. You will find thin films in bearings, maybe journal bearings, maybe rolling element bearings, maybe thrust bearings. You may find thin films in lamellas or between lamellas in clutches, wet clutches. And I, who myself is very interested in skiing, will probably find thin films, or partial at least, between the ski and the track when I ski. In our human joints is another example, and it's detrimental for the lubrication of those. When we drive our cars on the road, we may experience water hazard, and here we also have a thin film flow problem. And seals is another very important thin film flow and, well, actually percolating porous media flow also may be found. So thin film flow is really just fluid mechanics of thin films. Here we have an example which highlights how narrow the gap between the components, between the bush and the journal, the shaft, is in a journal bearing. So if we zoom in a small segment on that journal bearing, hopefully we have a fluid film separating the two surfaces to protect them from wear, to reduce the friction and therefore the power consumption. In this case, it's only the journal that is moving, indicated by the arrow here, but maybe so that both surfaces be moving relative to each other in thin film interfaces. So what we want to achieve really with a thin film approximation is to reduce the generalized Navier-Stokes equations that we were deriving before into a simpler system which can be integrated into a dimension reduced form. Now it turns out that scaling is required. required so that the partial derivative of pressure with respect to the cross-film coordinate z is 0, while we should preserve the pressure gradients in the other directions. So these components, they are found in the linear balance of the linear momentum equations. Now we will derive the thin film approximation, but for the sake of simplicity we will consider the incompressible and isoviscous 2D problem. And with isoviscous we mean that the viscosity will not vary with the pressure. Did I mention it was a 2D problem, so we will only consider a 2D problem. Now, a thin film, mathematically speaking, what is this? And here I had some coordinate axes. So for the 2D problem we have x and z axis, for example, and the z axis is the cross film coordinate and the x axis is the one that follows the film. We introduce some dimensions. We take first L node as a characteristic length of our lubricated interface, and then we take H node as a characteristic height or thickness of it. Then mathematically we can of course use the ratio between them, H node over L node, to moderate the thickness of the film. And since this will be a very small parameter, we use epsilon to denote it. And we will then make use of H node and L node to scale our independent variables x and z respectively. And that is what we will do next. When we scale, as you recall perhaps from the contact mechanics part, we scale only the independent and the dependent variables. Input parameters, they will become part of the non-dimensional groups of parameters that we will find in our dimensionless system of equations. And you remember these, we saw specifically the Hertzian ones, for example, in contact mechanics. Now, in this case, we have three independent variables, and those are the x and the z coordinates plus time. Now, dependent variables will be the velocity in the x direction, u, and the velocity in the z direction, w, and then we will have the pressure, which is treated then as the mechanical pressure. Now, input parameters are, as we see here in general, both surfaces may be moving, so we have to take both u1 and u2 as input parameters, and we have a constant viscosity of our lubricant denoted by mu A, and we have a constant density in our fluid, which is rho A. So then we scale our independent and dependent variables to obtain the set of non-dimensional variables. So non-dimensional x is obtained by scaling x with L node, non-dimensional z, scaling z with H node, t with T node, u with U node, w with W node, and p with P node. For incompressible and isoviscous flow in 2D, the continuity equation is just du dx plus dw dz equals 0. And if we use the scaling that we introduced before, we can just scale u with U node and then we replace u in the continuity equation by u naught times u bar, which you can see has been done here to the first term, and we replace x by L naught and the non-dimensional capitalized X here, and we do the same with the speed in the Z direction and the Z direction, and we have these two equal to 0, which means that we can multiply this equation with L naught over H naught if we like, to get a clean first term, just a dimensionless derivative term there. And then on the second term we observe or note that we have H naught over L naught is epsilon, and therefore this is actually just V naught over epsilon U naught. And now epsilon is a small number, and if we really let epsilon go to 0 here, this will blow up, you can see. So the only meaningful solution in terms of scaling here is to set W naught equal to epsilon U naught, and then the dimensionless continuity equation remains as it were in the dimensional form above, as you can see, and therefore we have a solid basis to continue from here. Now the x momentum equation for flow in 2D, it is this one, and if we now include that the fluid is incompressible and isoviscous, then we have that the density is constant, so we denote that by rho A, and we by the continuity equation we have the u dx plus the w dz equals 0, and therefore this term, the third term on the right hand side, is 0. Moreover, the rest of the equation can actually be simplified quite a lot, because it's isoviscous, then the viscosity is mu A, can be denoted mu A, and we can just take it outside the derivatives, and then we get this expression. We now note that we can change the order of the differentiation. So instead of differentiating with respect to x first or z first, we can switch the order, and we can get the following expression, where we have made use of this in the third and the fourth term, and the third term in the equation in the row above was actually just the second derivative of u with respect to z. And now we further notice that what we have here is actually d dx of the continuity equation, but the continuity equation is 0, says that the u dx plus the w dz is 0, and therefore what remains is just the viscosity mu a, constant viscosity mu a, times the second derivative of u with respect to x and the second derivative with of u with respect to z. Now, similarly, as we saw for the x momentum equations, we have the z momentum equations reducing when we consider the flow to be incompressible and isoviscous. And first of all, of course, we have the first term or the third term in the right hand side equal 0 here, and then also if we expand the fourth term and fifth term and join them together, we can, in the same way as we did before, change the order of derivatives. And of course take the constant viscosity outside the whole bracket and change the order of the derivatives to finally come to the equation that we have here on the bottom right, saying that the right hand side, the three terms in the right hand side equation above here must reduce to just mu a times the Laplacian of w. And if we now consider both of the equations simultaneously, this is what we had here on top, and then when the fluid is considered to be incompressible and isoviscous, the system reduces and becomes the one we see below. And therefore we can start the scaling procedure. So we had the scaling, same as before of course, and then the non-dimensional form of the 2D Navier-Stokes equation may be stated like this, by just replacing the dimensional quantities by the reference parameters times their non-dimensional representatives. Okay, so of course this looks very messy to start with all the reference parameters entering the system of equations. But let's consider now a few facts that we know. First of all, we know that epsilon is the ratio between H node and L node. We can introduce this one. We know that the scaling, the reference parameters for parameter for W is related to the reference parameter for U via epsilon, like this, and we can choose the time reference parameter to be the length of the domain over U. I will come back to what that means, but if we choose it like that, we have the set a little bit more specific, more specified set of reference parameters than we had before, because we know all these small connections. And then the non-dimensional form of the Navier-Stokes equation can be written like this, which is now, okay, still it looks perhaps a little bit messy because of all the reference parameters, but it's possible to handle, no problem. So in regard to the choice of the reference parameters for time, choosing it as L node over U node means that we consider only time events to be of the order of the time it takes for something to pass through the conjunction which has length L node with the velocity U node. For more details supportive of this choice, the reader is referred to the paper by Dawson in the reference given below. With this, and then multiplying the x momentum equation at hand with this fraction marked in red, now gives us a new way of formulating the equation looking like this. And we can do similar to the Z momentum equation, for which we will get this equation instead. And now we note that what stands in front of both these terms is partly the Reynolds number, which is the ratio between the inertial and the viscous forces. And in this context it is defined precisely like this. So we have the constant ambient density and the the constant ambient viscosity and the reference parameters for U and L, for speed and for the length of the contact. What is also very important to notice is that these terms that are related to inertial body forces are not only scaled with the Reynolds number R, but also in the X momentum equation it's scaled by epsilon squared and epsilon to the power 4 for the Z momentum equation. And we realize that for a film to be considered as thin, then epsilon must be small, typically 10 to the power minus 2 or in that order, or even much smaller. And then the inertia, the effect of inertia in a thin film must be very small, even though the Reynolds number itself may be quite large. So with the Reynolds number incorporated, like this, we get the X and Z momentum equations formulated here in non-dimensional form, and now we have nearly no reference parameters left except for the ones that scales the pressure gradient and the ones hidden in the Reynolds number, of course. So in order to achieve that we have the PdZ equals 0 while preserving the PdX in the equations, we see that we must choose P0 to be proportional to epsilon. So let's define that proportionality by this relationship. So P0 is proportional to epsilon to the power k. And then it remains to find k. Let us just introduce the relation C epsilon k for P0 into the equation. Then we have the following two momentum equations. We see that if we now further expand this relationship by precising k to be minus 2 plus a with alpha, with an alpha greater than 0, then we get this system. Now it's very clear that if we neglect all the terms, we will only have the second derivative with respect to z of u left. So we will have u to be a linear function of z. And of course this may be a very special case of some type of flow situation like plain Couette flow with a Newtonian fluid and so on. But it's not what we want to have. We need to preserve the PdX also in the equations. So how to do that? Well, okay, let's consider the second opportunity. So we have k equal to minus 2 minus alpha, where alpha is greater than 0. Then we get the following system of the simplification. And it is now clear that if we neglect terms of order epsilon, then what will be left is only the PdX equals 0. And that would also lead to a non-interesting system. Okay, to preserve now the PdX, well, in the X momentum equation, and to have the PdZ equals 0 in the Z momentum equation, when we neglect the terms including epsilon, then there is only one possibility. Alpha must be 0. And when alpha is 0, these are the terms that cancels out in the X momentum equation. And we can clearly see we have preserve the PDX by also having the second derivative of the dimensionless x component of the velocity with respect to z. Then in the z momentum equation we only have the PdZ left, meaning the PdZ is 0.